Today we're going to solve this problem. You flip a coin and roll a die. Describe the sample space of this experiment. Part B says, now each of 10 people flips a coin and rolls a die. Describe the sample space. How many elements does it contain? Part C, in the experiment of B, how many outcomes are in the event where nobody rolled a 5? How many outcomes are in the event where at least one person rolled a 5? Let's get started. For part A, we need to describe the sample space. Remember that the sample space is the set of possible outcomes. So somehow I need to encode the outcome of this experiment mathematically. So if I flip a coin and roll a die, then I have two results. So I might think to use a coordinate pair x, y, such that x belongs to, let's say, this set heads, or I'll denote this set heads and tails with a capital H and a capital T, and y belongs to the set 1, 2, 3, 4, 5, 6, which represents the outcome of the dice roll. Okay? So, for example, if I got heads on my coin and I rolled a 3, then this would look like H, 3, and that's one outcome which belongs to my sample space. Okay? All right, now let's look at part B here. So now each of 10 people flips a coin and rolls a die. Describe the sample space and describe how many elements it contains. So the sample space is essentially 10 different outcomes, each of this form. So one way to encode this would simply be omega to the power 10. This isn't a normal exponent that you might be familiar with. This just means the Cartesian product of omega with itself 10 times. Okay? So, well, what does the Cartesian product mean? Well, this essentially means that, well, this is a simple example of a Cartesian product. This means that we're essentially looking at coordinate pairs where each coordinate takes a value in omega. So, for example, an element of this Cartesian product might look like, for example, say the first person rolled heads or flipped heads and rolled a 3. The second person flipped tails and rolled a 2. Third person, let's say, flipped tails and rolled a 6, etc. And then the 10th person, let's say, flipped heads and rolled a 1. Okay? So notice that this element here, let's call this omega 1. So omega 1 belongs to the first copy of capital omega in my Cartesian product. If I look at this second outcome of the second person flipping tails and rolling a 2, then this outcome belongs to this copy of our sample space, and so on and so forth. And so I end up with a coordinate, not pair, but a coordinate tuplet consisting of the outcomes of each person conducting the experiment. Okay? So this is the correct, or one correct way to describe the sample space. Okay? So long story short, the sample space is simply our original sample space raised to the power 10, where this power is with respect to the Cartesian product. Now, how many elements does it contain? Well, to answer that question, we need to answer the question of how many elements does the original sample space contain. So the original sample space is going to contain 2 times 6 different elements, so namely 12 elements, okay? So I could enumerate those elements. One way to see that is by looking at a matrix and then enumerating each possible element. Let's say I'm going to label the columns by head and tails, so there's 2 columns, and then the outcomes of the dice roll are 1, 2, 3, 4, 5, 6, so there's 6 possible outcomes of the dice roll, and then basically each entry of this matrix represents a possible event. So for example, this entry of the matrix represents the event that I flipped a tails and rolled a 2. Okay? So the size of this matrix, well, how many elements does it contain? Well, it contains 2 times 6, so 12 elements. Okay? Another familiar reminder that multiplication of numbers corresponds to area. Now, if I look at omega to the power 10 and I ask how many elements does this sample space contain? Well, all of a sudden, if I look at an arbitrary element in omega to the 10, then I know that there are 12 possible choices for this first entry, 12 possible choices for the second entry, etc. All the way to the 10th entry, there are 12 possible outcomes. So this suggests that, in fact, the cardinality of omega to the power 10 is simply 12 raised to the power 10, where now I'm actually raising the number 12 to the power 10 in the usual sense. Okay? Wonderful. So now, let's attack part C. In this experiment of part B, how many outcomes are in the event where nobody rolled a 5? Okay. So, if nobody rolled a 5, and I'm guaranteed this information, then I know that it's essentially like deleting this number 5 from my sample space. And if I delete the number 5 from my sample space, I do the same arithmetic and recognize that the new cardinality of my sample space is now 5 times 2, which is 10. Okay? And so let's raise the board here. So omega prime, let's say, this is going to be the set, it's going to be a subset of our original set, and it's going to be the set of x, y, such that x is still allowed to be heads or tails, and now y the outcome of the die roll must belong to this set 1, 2, 3, 4, 6. So I'm not allowed to roll a 5. And so the cardinality of this set is now 2 times 5. So the cardinality of omega prime is 2 times 5, which is 10. And then by the similar logic, if nobody rolled a 5, then omega prime to the 10, which is a subset of omega to the 10, where omega to the 10, remember, this is omega cross omega 10 times. So if I raise omega prime to the power 10, then this is precisely the subset of omega to the 10 such that none of its elements contain a person rolling a 5. So an element of this, an element of omega prime to the power 10 is a tuplet omega 1 through omega 10, where each of these elements of this tuplet belong to omega prime. In particular, each of the elements of this tuplet represent the outcome of a person performing the experiment and not rolling a 5. Okay? So, then by the same logic as the previous problem, we can recognize that the cardinality of omega prime, raised to the power 10, this cardinality is 10 to the power 10, okay? So this is the number of outcomes where nobody rolled a 5. Okay? And then the last part of the question was to determine the number of outcomes where at least one person rolled a 5. Well, this is actually simple because this is the disjoint. So if I want the number of outcomes where at least one person rolled a 5, this is precisely the complement of the number of outcomes where nobody rolled a 5. Namely, if I look at 12 to the power 10, which is the total number of possible outcomes, and then I subtract all the outcomes where no one rolls a 5, then this is the number of outcomes where at least one person rolled a 5. All right, and this is just a more general fact in probability theory that if I look at the probability of some event happening, let's say the probability of A happening, so if A is any event, then if I add the probability of A and the probability that A happens and the probability that A doesn't happen, so the complement of A, then I get 1, okay? Or in general, the cardinality of a set, A, and the cardinality of its complement are equal to the cardinality of the whole space, all right? So once I've determined the number of outcomes where nobody rolled a 5, then this event, which is the logical opposite of this event, so either this event happens or this event happens, and they're mutually exclusive events, meaning that one of them happens, at least one of them must happen, and if this event happened, then this event cannot happen. If this event happens, then this event cannot happen. So we say they're mutually exclusive or disjoint events, and one of them is guaranteed to happen. So that means that, you know, if I know the cardinality of one of the events, the cardinality of the opposite of the event, or the complement of that event, is simply the total number of possible events minus the number of events belonging to this, the number of outcomes belonging to this event. All right, I got a little bit tangled up in the words here. So let me know in the comments if I could have improved this lecture. And thank you for watching.